Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to have Xiao Liu here to come to give us a talk on TCP and P2P, supporting future internet from layer 4 and layer 7. Xiao got his bachelor degree from Beijing University in year 2000. From 2000 to 2007, he is at OSU IUC and get his master and PhD degrees. From 2006 and 2007, Xiao is also with Windows networking group of Microsoft, working on quality service issues in Windows networking. From year 2007, Xiao became a postdoctoral researcher in Princeton University. He is also a visiting researcher for the Communication and Collaboration System Group, working with Phil and me on a number of peer-to-peer related issues. Without further ado, let's hear from Xiao about his PhD and postdoctoral work on various issues.
Thanks, Jim, for the introduction. Good morning, everybody. Thank you and welcome to this talk. Today, the talk is on TCP and P2P, supporting future internet from layer 4 and layer 7. As you know, as Jim has already introduced, I'm Xiao Liu, and currently a postdoc in Princeton and visiting researcher in Microsoft Research, and graduated from UIUC. Now let's have an overview of my past work. My PhD career is mainly on TCP and congestion control, and my work in this area was on two directions. The first direction is on protocol design side. I designed 3 protocols, 2 in TCP side, 1 in router side. The 2 TCP side protocols are TCP-Illinois and 4CP. TCP-Illinois is a TCP variant for high-speed networks. 4CP is a TCP variant for low-priority users, especially decrement and FTP download. And for the 4CP work, I won the Best Student Paper Award in IW course. And for the router side, I designed one protocol called exponential read. That is the first red-like router algorithm, which can stabilize all TCP variants. And besides the protocol design part, I have also performed a lot of analytical study on the congestion control system and on the modeling of congestion control system. My main work include the new development on stochastic matrix model, and from this model, analyze the stability and fairness properties of all kinds of TCP protocols. And also, I have proposed a new class of primal dual algorithms and performed the stability analysis. Finally, I have done some work on the modeling of delay in fluid model and pointed out some pitfalls of the old modelings. After I graduated from UIUC, I joined Princeton, and for collaboration purpose, I'm also visiting researcher in MSR. And the joint project is on P2P streaming. Basically, our existing work focus on the streaming capacity of a P2P system. We start from a special IPTV case and then extend to more general case. So that is an overview of my work. And in this talk, I will focus on 2 topics. The first is on TCP-Illinois. The second is on streaming capacity of P2P. Now let's first have a look to the first half on the TCP side. We know that TCP is the current internet congestion controller. It is a window-based algorithm, and it chooses packet loss as a congestion signal. The key component or key algorithm for TCP congestion control is this ARMD algorithm. Let's have a look to this figure. This is the additive increase phase. If there is no packet loss, TCP increases their window size linearly. Here, that is the multiplicative decrease part. If there is packet loss, TCP backs off their window size by a fixed proportion. TCP has been very successful in the past 2 decades. It has avoided the global collapse, which is a big problem before TCP congestion control was introduced. And furthermore, it allocates the low-speed networks both efficiently and fairly. So TCP was successful in before. However, in the future, high-speed networks, TCP may not be successful. The major problem is that it is not efficient in high-bandwidth delay product networks. Its utilization can be very slow, very low. There are two reasons for this low utilization. First, let's have a look to this period. That is the period between two congestion losses. We call this period recovery time. And due to the TCP's very slow increase, this recovery time can be very long. In some gigabps networks, this recovery time can be hours. That is not desirable. Second, from this ARMD feature, we have a fixed relationship between packet loss probability P and window size W. Excuse me. For any network media, there is a transmission error. In typical fiber networks, the transmission error probability is lower bounded by 10 to -7. So the packet loss probability is lower bounded by this value. And from this relationship, we know that for TCP, its window size is upper bounded by this value. Therefore, even if the network is very high speed and can hold a much larger window size, TCP cannot achieve a window size larger than this value. Combining these two vectors, TCP utilization in high-speed networks is generally very low. And in some special cases, it can be less than 20%. So we know that for high-speed networks, we need to modify TCPs. There are some existing TCP modifications. And in general, the prior work can be classified into two classes. The first is loss-based algorithms. Examples are HSTCP, scalable TCP, and HTCP. For these algorithms, similar to TCP, they still use packet loss as congestion signal, but different from TCP, they use a higher window size increase. Basically, they increase their window size faster than the traditional TCP. As a result, they can get a smaller recovery time, and their utilization can be much better. However, this loss-based algorithm have some fundamental problems. Since their window size increase much faster than the traditional TCP, the number of packet losses becomes much larger than old TCP Reno, and heavy congestion is incurred. As a result of this heavy congestion, we can show that this kind of algorithms, they have some problem for fairness and compatibility issues. I will explain that in detail later. There's another class of algorithms. They use queuing delay as congestion signal. Examples are TCP Vegas and fast TCP. For these algorithms, they decrease their window size if the queuing delay is large, and increase their window size if the queuing delay is small. For this kind of algorithms, they can achieve a very good throughput, and their fairness property is also very good if everybody uses this new protocol. However, these delay-based algorithms, they have some fundamental problems. Mainly, there are two. The first one is that they are incompatible with current TCP Reno. If we put two users, one use TCP Vegas, one use Reno, and put them in the same network link, then almost all the network bandwidth was taken by TCP Reno, and TCP Vegas almost get nothing. So there is a backward compatibility issue for the delay-based algorithms, and they are not good for incremental decrement.
So where does BIC and QBIC and CTCP fit in this?
I will introduce these two and compare with my protocol later. CTCP fits in the loss-based, big TCP fits in the loss-based algorithms, and CTCP combine both loss and delay. I will introduce that later. So now let's have a look to such a summary. For a good TCP replacement, it should satisfy at least these four requirements: efficiency, fairness, compatibility, and robustness. The TCP is bad in efficiency, so we have some modifications. Loss-based algorithms, they are good in efficiency and robustness, but not very good in fairness and compatibility. Delay-based algorithms, they are very good for efficiency and fairness, but they are bad in robustness and very bad for compatibility. So the challenge or the question is, how can we design a TCP which satisfies all these four requirements? TCP-Illinois is such an algorithm.
Compatibility, you're really talking about fairness compared to other algorithms.
Fairness compared to old TCP Reno. So basically, fairness here, that is RTT fairness.
Fairness
within intra-protocol, the fairness against the large RTT users, and compatibility is inter-protocol. And TCP-Illinois is one such algorithm which satisfies all the four requirements. From our previous analysis, we see that neither pure loss nor pure delay-based algorithm, they are perfect. So our natural idea is to, why not combine both loss and delay? So we come up with this original idea. This work is at the same time with CTCP, and both TCP-Illinois and CTCP choose to combine both loss and delay, and they are independent work. However, their method of combining loss and delay are totally different. We will compare that later. Now for TCP-Illinois, its idea is that it uses packet loss as a primary signal to determine whether we should increase window size or decrease the window size. For example, if there's no packet loss, we can increase our window size, and for packet loss, we decrease the window size. And it uses a queuing delay to adjust the amount of window change. For example, when the delay is small, we can increase our window size fast. If delay is large, we should increase our window size very slowly. So that is notable thing is that loss is a primary signal, and the delay is only the secondary signal. By combining both loss and delay, TCP-Illinois can achieve a concave window curve, which I will show very soon. And also it satisfies all these requirements. And TCP is the first such algorithm which have a concave curve and satisfy all the requirements. For some recognition and achievement, TCP-Illinois was widely acknowledged in both industry and academic side. For industry side, it was selected by Linux Foundation and was already implemented in Linux kernel after 2.6.22 by Stephen Hamilton. And academic side, it was running up in the Best Paper Award in Value Tools 2006.
I recently went to John Ree's talk, and he said he's got it distributed in Linux. So which is implemented and which is distributed? Maybe there's more than one Linux. Can you clarify this? That is the Linux kernel provided by Linux Foundation, and for most commercialized Linux release, they choose the Linux kernel provided by Linux Foundation, and they can have their own application layer modifications, their own fancy stuffs, but the kernel, most thing is adapted from this Linux kernel by Linux Foundation.
I guess you can have multiple implemented, but only one that's on by default. My understanding is Cubic is on by default.
Yes, Linux actually implemented 7 to 8 TCP variants, and they can test all these variants and compare. So let's continue. It was also the run-up in the first Delaybased Illinois Student Invention Prize. That is competition among all UIUC students. My invention of TCP-Illinois was ranked number 2 among all the UIUC students. And now let's have a look to the concave window TCP-Illinois achieved. We know that traditionally TCP Reno chooses a linear curve, and the main problem is that it has very slow recovery time and very low utilization. And later algorithms like HSTCP, they get a convex curve. That is because the window increase speed becomes larger as the window size itself becomes large. And we think that this convex curve is not ideal. The major problem is that when congestion occurs, the window increase is very fast. So there are a lot of packets injected to this network, even after the network is already congested. So there are a lot of number of packets, they get dropped, and the congestion we face is very heavy. And from our analysis, heavy congestion leads to unfair resource allocation among different RTT users. So that is a major problem of this convex curve. And TCP-Illinois, on the other hand, gets such a concave curve. The reason is because when far from congestion, the delay we measure is very small, and we can increase the window size very sharply. And when close to congestion, we can measure a large queuing delay, and then we reduce the window increase speed. As a result, we get this concave curve. And if we compare these three curves, we see that this shaded region, this shaded region, this shaded region, they correspond to bandwidth lost. And this region, this region, this region, they correspond to packet losses or the congestion heaviness. So comparing these three, we see that this concave curve is best in both bandwidth lost and packet losses. So combining these two, we can have an intuitive picture of TCP-Illinois. Since they have a very small bandwidth lost, they are more efficient than the older TCP Reno. Since they have small number of packet losses, as our analysis indicate, this will bring to a very good fairness property. And since the window size initially increases fast and later becomes lower, if we think of an average window increase speed, it's not too fast. It's not compared with old TCP Reno. It's not very too fast. So it has a good compatibility property if we consider the backward compatibility with TCP Reno. And furthermore, since delay is a second-order signal, the noise buried in delay has only second-order effect. So TCP-Illinois is also robust. For all these properties, we will support them by analysis and simulation later.
So in this graph, you showed the available bandwidth as being a constant, meaning a horizontal line.
Yes.
If the available bandwidth underwent a sharp decline, then it seems like you cause greater congestion because the slope is steeper for when the actual value drops.
Yeah, that's a great question. Actually, for example, if in this cycle the available bandwidth is here, in that cycle available bandwidth becomes to here, then it will. Not necessarily, because before congestion occurs, it sees a larger queuing delay, and it will increase the window size very slowly, and the overshoot is very small. The curve will look like this.
But that depends on whether the available bandwidth, how rapidly it declines, right? If it declines in less than an RTT, then you don't have enough time to get the delay feedback, right?
Yes, but if two congestion events within one RTT, typically we treat them as single congestion event. And this sharp increase is not immediately. It will wait for at least one RTT time to start this sharp increase. So we have some later simulations shows that if the available bandwidth keep changing, always TCP-Illinois can keep a very small overshoot and increase to close to available bandwidth very quickly. And after we proposed this concave curve, later it was shown that this concave curve is actually optimal. If we think of congestion control as a stochastic optimal control with incomplete network information. And this optimal is in the sense of maximize benefit minus cost. Here, the benefit is associated with our bandwidth, and cost is associated with every packet loss. So to analyze TCP-Illinois and also other TCP variants, we have developed a new stochastic matrix model. And from this model, we can analyze the stability and fairness properties of all TCP variants. And we know that before, or traditionally, people use fluid model to analyze congestion control system. And in the fluid model, it does not model the randomness in the networks, and they can treat the flows as a fluid. And they also use a single congestion signal. As a result, it cannot analyze these two problems. First, if a protocol combines both loss and delay, you have two congestion signals. The old fluid model cannot analyze this kind of algorithms. Second, in the internet, it's possible we see a synchronization behavior, and TCP and fluid model assumes no synchronization, so it cannot answer the two questions: when will synchronization occur, and if synchronization occur, what will happen? So to conquer these two difficulties, recently there was a new model introduced, that is the stochastic matrix model. We have developed this model and make some new extensions and modifications. Basically, this model considers the randomness in the packet losses in this congested network link. And with this randomness considered, the window vector of all the users' window size, they evolves as a Markov chain. And we can use Markov chain technique and stochastic process to analyze the behavior of these window sizes. And with this model, we can analyze a protocol which combines both loss and delay, and that is only approach if we wish to know the impact of synchronization. And the main contribution of our new development in this model is that for the first time, we showed the following relationship. The window increase speed right before congestion, this will determine the congestion heaviness, or in another way, the number of packets dropped when congestion occurs. And this congestion heaviness will determine the synchronization level. That is, how much % of users will see packet loss at the same time and reduce their window size at the same time. And this synchronization level further determines the fairness property. In particular, if a protocol increases their window speed fast before congestion, they will see heavy congestion, and the synchronization level is high, and which lead to a bad fairness property, and vice versa. For TCP-Illinois,
Since its window increase before congestion is very slow, it has very light congestion and very low synchronization level, and it has a good fairness property. As a comparison, the convex curve like TCP, they increase their window size fast before congestion, so their fairness property is worse than TCP Reno and TCP-Illinois. Now let's have a look to some we have performed analytical study from stochastic matrix middle, and also we have performed extensive NS2 packet level simulations. NS2 is widely believed to be the best simulator for wireline networks, and all the congestion control and TCP community, they use NS2 to test their algorithms. And all the conferences and journals, they accept NS2 simulation results. Here are some simulation results. This is the window curve for 4 TCP-Illinois users. They share the same link. So from here, we see that each TCP user, they see the concave curve in each phase. And here, since we have 4 users, for one particular user, the available bandwidth keeps changing. So we see that it always becomes a concave curve. And if the available bandwidth is here, before it is close to available bandwidth, the increase becomes low. And when somebody backs up, we have more available bandwidth, then we can increase sharply, and then becomes low again. So it keeps this concave curve, increase sharply and slow, until everybody can get this bandwidth very, both allocate the bandwidth effectively and fairly. And in the right figure is a comparison of TCP-Illinois and TCP Reno for fixed packet loss probabilities. The red curve is for Illinois, and the blue curve is for Reno. Clearly, for fixed packet loss probability, TCP-Illinois has much better utilization than TCP Reno. Now, let's answer the question on CTCP and big TCP. I will briefly introduce these two because they are popular nowadays.
On the previous graph, are there some assumptions about bandwidth delay product that's making a big difference there?
Here? Yeah, this assumes that the bandwidth is very high, and the packet loss probability determines the window size.
So, what is the bandwidth delay product for that?
For this case?
Yeah. How big does it have to be before you see such a gap?
Excuse me. That is for huge, for such big gap that can be seen in huge gigabps level of networks. Okay, let's briefly introduce CTCP and big TCP. And we know that CTCP was implemented in Windows Vista, and it is also a protocol which combines both loss and delay. However, their combination of loss and delay are fundamentally different from TCP-Illinois. Essentially, CTCP used delay or loss in different stages. Here we have a simple curve of CTCP. Originally, it mainly used loss and have a window curve similar to HSTCP. And then it mainly used delay, and the curve is similar to Vegas. And then it goes back, mainly use loss, and the curve is similar to TCP Reno. So that is a window curve of CTCP. And through simulation comparison, we can see that CTCP, for fairness, compatibility, and robustness, TCP-Illinois is better than CTCP. We will show the simulation comparison soon. Now let's have a look to big TCP that is implemented in Linux, and I believe it is the default mode for Linux TCP. And big TCP only uses packet loss as congestion signal. It has 2 stages. One is binary search, and another is max probing. This is a typical curve for big TCP. Suppose the old available bandwidth is 100, and after a packet loss, it will drop to 50, and then use a binary search. Use a log curve to increase quickly to around 100 and stay around 100 for a longer time. If after stay around 100 for some time and does not see any packet loss, it will predict that we have more available bandwidth. Suppose the new available bandwidth is 200, then it chooses an exponential curve to prove the new available bandwidth. So it's a curve of big TCP is first concave and later convex. Due to this feature, if the new available bandwidth is higher than the old available bandwidth, then before congestion occurs, the window increase is very sharp. And from
our analysis, we have already mentioned that this sharp window increase before congestion is not desirable for fairness property. It can make a bad influence for bad fairness property. As a comparison, this is a window curve for TCP-Illinois. Even if it backs off from 100, it does not go to 100 very quickly. Instead, it will prove the new available bandwidth and increase to new available bandwidth very quickly, and then the increase becomes low before new available bandwidth. And if we check the window increase, this slope, it is much slow and much gradual. So TCP-Illinois has a good fairness property.
Intuitively, the reason it can do that is because it's looking at delay.
Yes.
Loss.
Yes. Because it can use delay information to predict how imminent is the congestion, how far away from congestion, and how far away is the available bandwidth. So from this curve, intuitively, we can see that TCP-Illinois has a better fairness and compatibility property than big TCP. Now let's compare that.
You mentioned that big TCP is the default in Linux, and I wonder why they don't choose loyal.
I think the main reason is because big TCP was proposed much earlier than TCP-Illinois. And before TCP-Illinois was proposed, they have already chosen big TCP as the default. And TCP-Illinois was just recently included into Linux kernel, and they were in the testing stage. And they plan to do a lot of extensive internet testing.
Seems too perfect to be true.
From the analytical model and from simulations, it looks indeed very perfect. But we have not done a lot of testbed experiments, so we don't know its real performance. But at least from analysis, from intuition, and from extensive NS2 simulations, it looks like a perfect algorithm.
I think the one that's on by default on Linux is cubic, which I don't know the distinction.
Yeah, cubic is similar to. Yes, cubic is also developed by the same authors as big TCP, and the idea is similar. For big TCP, this is a log curve and then an exponential curve. And cubic TCP changed this log curve to an exponential curve to a cubic curve and a square root of a cubic square curve. So it's only a minor change of big TCP. Basically, they are the same class, and the performance is very similar. So now let's compare the performance of TCP-Illinois and CTCP and big TCP for the fairness and compatibility issues. Here, this is a figure for the window size of 4 TCP-Illinois users with different RTTs. It clearly shows that all these users, their window size is a similar level, and that is the same fairness property for TCP Reno. And here, that is a compatibility comparison. We have 2 Illinois users and 2 Reno users. We see that they are almost in the same level. Also, TCP-Illinois indeed get a slightly better bandwidth. And this slightly better utilization provides incentive for the old TCP to switch to the new TCP. So, but anyway, old TCP is not suppressed too much, and we can see there are some sense of compatibility.
Have you done any compatibility analysis between this and either CTCP or this and cubic?
Yes, I will show that later soon.
Okay.
So in the bottom row, that is the simulation for CTCP. Here, it is CTCP for users with different RTTs. The RTT from 60 milliseconds to 120 milliseconds. And from here, we see clearly that the small RTT user, this dark blue curve, get a clearly better bandwidth than the other users. So
does that mean that they're getting less than they would get without it? Oh, sorry, I guess I'm asking about compatibility. You're talking about fairness.
okay, yes. Now let's go to the compatibility. These higher curves are for CTCP, and lower curves is for TCP-Illinois. For TCP Reno. So it's clearly that the gap between CTCP and Reno are very large. If you compare the gap here is much larger than the gap between Illinois and Reno.
It depends on what the parameters are. Right? If they were all like Reno, mentioned before, one of the problems is it leaves bandwidth on the table, right? It can't actually exercise all the bandwidth on a gigabit length because of the algorithm.
Yes.
And here, if the difference is just due to the fact that it's using up that unused bandwidth.
No. The difference is because CTCP chose a much more aggressive algorithm than Reno and suppressed Reno. For here, that is not a giga BPS link. This is for users share a 100 Mbps link. So basically, our aim is that when we show efficiency, we compare high-speed networks, and when we show if compatibility, we consider a current medium level networks, because that is only sense in the medium level we have coexistence of these two. And for this simulation, these 4 users share a 100 Mbps link.
Yeah, I want to question some of these things too. I mean, so you have 4 flows total, right? So what is that representative of? When on a high-speed link you have a gazillion flows?
Yeah, that's a very good question. In high-speed links, there can be a lot of flows, and we actually have performed extensive simulation results. Not only for this one, we have the flow number from 4 to 10 to 20, and this is only one example. For all the extensive simulations, there is a significant gap between CTCP and TCP Reno.
This compatibility problem happens when you scale up the number of flows.
If we scale the number of flows, the gap may be a little bit smaller. That is because the per flow bandwidth becomes less. If we scale the per flow, if we keep the same per flow bandwidth and scale the total throughput, the total capacity with the number of users, then it's hard to see such a trend. So that is a simulation result for CTCP. Now let's compare with big TCP. This is the fairness for big TCP, and this is the compatibility for big TCP. From here, it looks like the big TCP, the fairness is even worse than CTCP. And this dark blue curve for the small RTT users take a significantly larger window size than all the other flows. And that is the compatibility part. This higher curve is for big TCP, and low curve is for TCP Reno. And from this simulation study, it clearly is that both CTCP and big TCP, they surprise TCP Reno a lot. And if we define compatibility using a relative scale, not an absolute value, then we can say that TCP-Illinois is better than CTCP and big TCP.
So do you have indications of what happens when you put CTCP and big TCP on the same link? Do they?
It's not very meaningful, because when we say compatibility, it's only for the coexistence of old algorithms. So basically, the idea is that in the real world, we wish to introduce a new algorithm, and there are a lot of old algorithm users. It only makes sense to compare the coexistence of old and new. To compare two new, that is not that important.
That's the same question I was asking, is whether you're going to be comparing CTCP versus Illinois and Cubic versus Illinois.
I have not tested that.
Those are existing deployed algorithms, that if you're introducing a new one, those are the old ones. The old ones include CTCP, Cubic, and Reno right now.
Yeah, I think that's a very good suggestion. I will go back and do some simulation studies. I don't have simulation evidence to support that, but my belief is that it will depend on which protocol increase more sharply, more aggressively. The protocol which increase most aggressively will suppress other protocols. And for here, if we compare that, I tend to believe that these three, their window aggressiveness is in a similar level. So their bandwidth allocation should be in the similar level.
That's why I'm asking about CTCP versus big TCP in particular, is that if that's simply a reflection of how aggressively they're ramping up, then will we see essentially similar performance from all of them because they sort of suppress each other equally, or will there be some behavior like you're saying there where one of them?
I tend to believe that there is no unique equilibrium point. There is no unique allocation. It depends. There can be multiple equilibrium points, and the allocation depends on the how do we start this one first or do we start that one first. For example, if we see the window curve here,
all these algorithms, they have some curve increase fast, some curve part increase fast, some part increase slow, increase slow, increase slow. So it depends on which part and which part overlap. There are several existing studies performed by Kevin Tang in Cornell, and his study shows that if we put two protocols, one use loss and one use delay, then it's very likely that they will have multiple equilibrium points, and the resource allocation between these two depends on who starts first. So it's very likely that if we put peak TCP and CTCP, who performs better depends on who starts first. So that is also a possibility.
It just seems to me that that's exactly the problem, that you don't know who's going to have started first. And so there needs to be a metric of essentially the stability of allocation, meaning regardless of who starts first,
yes,
do you converge to similar places? Because if you do, then that indicates to me a good protocol.
Yes.
And if you don't, then that's maybe not a good protocol.
Yes, that is why that's part of the reason we think a pure delay-based algorithm is not good. Because if we put a pure delay-based algorithm with a pure loss-based algorithm like TCP Reno, the performance and the resource allocation are unpredictable. It depends on who starts first. So that is a compatibility issue. And that is why I claim TCP-Illinois is better, because it's mainly primarily use loss, and delay is only a secondary signal. And if we start TCP-Illinois and Reno, put that in the same network, no matter who starts first, the final convergence goes to the same operating point. So that is a comparison between Illinois and big TCP and CTCP in terms of fairness and compatibility.
I'm just really curious what happens when big competes with CTCP. Is it like the bottom one? Is it that bad?
No, surely not.
Compared
Yeah.
It will not be, the gap will not be too huge like this, because Reno is the least aggressive one, and any more aggressive one can suppress Reno more significantly or a little bit. For both big TCP and CTCP, they are more aggressive than Reno, so their gap should be much smaller. That is the sure thing we know. But who get a higher curve, that is unknown, and we need to do some simulation to show that. My prediction is that who get a higher throughput may depend on who starts first. So there's no unique operating point.
I could probably tell you for sure, but I think, but I'm not sure, that cubic steals a little bit from CTCP because it's more aggressive, less fair in the fairness metrics. So I think you'd see a smaller gap, but cubic would come out above and CTCP would come out as having a little bit stolen, but I'm not sure. I think Marari has done that analysis or worked with Kuhn or something that has, but I don't know.
Yeah, probably. That is because CTCP combine both loss and delay, and the big TCP only use loss. So if a protocol only use loss, it will always increase unless congestion occurs. But if a protocol use delay also, like CTCP, like in this part, it's mainly use delay. If at this phase, the big TCP is increasing, then the CTCP will always see an increasing delay and always decrease their window curve. So yeah, I agree with your opinion. Probably big TCP can get a much higher bandwidth share. But it also depends on the buffer length. If the buffer size is very large, then there is a trend that delay-based algorithm can perform better. So the main conclusion from Kevin Tang's work on the heterogeneous protocols is that if a loss and delay-based algorithm coexist, who get a better bandwidth depends on both who starts first and on the buffer size. A larger buffer size favors delay-based algorithm. So now let's go on and have a look to the robustness feature and compare TCP-Illinois and Vegas. Vegas is a typical delay-based algorithms, and it's widely known that Vegas is not compatible with Reno. It's widely known that Vegas is not robust against noise in the queuing delay measurement. The reason is because we cannot measure the queuing delay directly and accurately. Instead, we measure the round-trip time, and from the round-trip time trajectory, we estimate a queuing delay. This estimation is always buried with noise, And it's a question whether this noise is high or low. But indeed, people know that if this noise is large, then Vegas fails to work. Here, a simple simulation. We have two Vegas users sharing the same link. The red curve says no noise, and the yellow curve says noise. Clearly, the noise-free user gets a much higher bandwidth share than the noisy users. The reason is because delay is the first signal, and the noise in the delay has the first order impact on your window size. It's pretty possible that when you should increase your window size, you see a noise in delay and you decrease your window size. So that is for Vegas. As comparison, that is TCP-Illinois. This red curve is for the user without delay, and the yellow curve is the user with delay. And clearly we see that these two users get similar bandwidth utilization. And we see no fairness issue and no utilization issue associated with delay. The main reason is because delay is a second-order signal, and the noise in delay has only second-order impact. It does not change the window size, increase or decrease direction. If we check this fine scale of this yellow curve, we see that sometimes it increases faster, sometimes it increases slower, but with or loss, it will always increase. And if we check a larger scale, the curve is still concave. So basically, since TCP-Illinois use delay as a secondary signal, delay has only minor impact, and it only influences the fine time scale thing and does not change the larger time scale feature. So this comparison shows clearly that in terms of robustness, TCP-Illinois is much better than delay-based algorithms like TCP Vegas. Any question until now? Okay, now let's summarize TCP-Illinois. TCP-Illinois chose its original idea of combining both loss and delay, which is independent work of CTCP, and it chooses a different way to combine loss and delay. It uses loss to determine whether window size should increase or decrease, and it uses delay to determine the amount of increase and decrease. Further, since the delay is a secondary signal, TCP-Illinois is robust against the noise in delay. And also, TCP-Illinois achieves a concave curve. With this concave curve, it increases window size fast to the available bandwidth quickly, so it has efficiency. And before congestion occurs, the window increase is low, so it is fair and compatible. And TCP-Illinois is the first variant which can be shown to satisfy all these four requirements: robustness, efficiency, fairness, and compatibility. And it is suitable for large-scale TCP replacement. There has already been some TCP replacement, and they are suitable for some special users or dedicated users like fast TCP. But if we seek a general TCP replacement that every machine in the internet can change, we believe that TCP-Illinois is the best candidate for such a TCP replacement. And from simulations and analysis, it outperforms other TCP variants. And it's also implemented in Linux kernel already.
So the curve increase depends on the sense the delay and loss. I imagine there would be some parameter controlling the rate increase, how much.
Yes.
And I don't see any discussion on that.
Yeah, that is. Yeah, I can show you later. I can show you soon. It is some too detailed work, so I go to some other places, but I will show you the curve here. Here, this shows excuse me, the more details of TCP-Illinois. This alpha is window increase speed. Initially, it is very high, around alpha max, if queuing delay is less than a threshold. And then, as queuing delay increases, it drops very sharply. And finally, if the queuing delay is very large, it is around alpha min. And typically, for standard setting, alpha max is 10, and alpha min is 0.3. And we know that for TCP Reno, alpha is always 1. So TCP Reno alpha is always here, and TCP-Illinois choose such an alpha curve. So the increase is like originally before congestion, when far from congestion, it increased 10 times faster than TCP Reno. And when congestion is close, it can increase the increase drops quickly and becomes similar level to TCP Reno.
So these parameters are optimal for all kind of network conditions?
These are for standard. TCP-Illinois, although it has these parameters, it works well for a large range of parameters. I have switched the parameter values. The parameter only have minor influence. These parameters are generally for the 100 megabps to 1 gigabps link. Even if it is outside this range, it still performs very well. So basically, if we change this parameter from 10 to 20 to 5, this 0.3 to 0.5, 0.7, the difference is minimal. So it is very robust against the parameter setting.
DM is what?
DM is the maximum queuing delay it ever measured. So basically, TCP-Illinois measures all the RTT trajectory. And for the minimum RTT, we think that is propagation delay. And the maximum RTT minus the minimum RTT, that is this DM. That is the maximum queuing delay. And the current RTT minus the minimum RTT, that is the current queuing delay.
So if you set all these to 1, does it force it to behave like Reno?
Yes, correctly. If both these two parameters are 1, it is the same as Reno.
I guess what's surprising is the claim that on every dimension this dominates the other TCPs. Like I know the CTCP guys try to be not too aggressive, and they gave up other things, I think.
Yeah, I agree that it's not in every domain. When we say it is better than others, it is in a comprehensive comparison. If we combine efficiency, fairness, compatibility, and robustness. For example, if we purely think of utilization, the delay-based algorithm, they are the best. For example, fast TCP and Vegas. If by itself, and if the delay is, if the noise in delay is not an issue, they can get 100 utilization. They have the best performance in purely utilization. And big TCP, if purely for utilization, since in general their increase speed is faster than TCP-Illinois, they may also be slightly better. But if we comprehensively consider all these 4 requirements, we believe that TCP-Illinois is best.
So are you going to submit this to the ICCRG to evaluate?
We already published the work and contact and have co-worked with Linux Foundation people and put that into Linux. And we also plan to make RFC to standardize that, and also work with Linux Foundation people to do more extensive testbed experiments.
So one of the problems that industry perceives is that Linux puts in things that has not gotten any stamp of approval from anybody other than whoever sticks into the Linux distribution, which does not have a great deal of evaluation compared to other things. And so the ICCRG is the research group that has a bunch of researchers in it that evaluate protocols.
Okay.
And they just finished the CTCP one. I think they're doing Cubic next and something like that.
Okay.
That the goal is for them to evaluate the criteria outlined by Sally Floyd in the criteria for evaluations document, and to make some statement as to whether it is safe for use on the global internet or only safe for use within some restricted contexts or what. And so CTCP has just completed that. The stuff is about to be delivered, and it's only waiting for updates to the internet draft to clarify some things that they asked questions on that was slightly ambiguous in that draft, and so the draft needed to be updated. And so they were holding off submitting that until the draft had those clarifications in there to say what it actually does. And so that should happen within the next week or two, and then the ICCRG will deliver that report to the IETF that says this is safe for deployment on the global internet based on all of the evaluations and stuff that the various researchers did. And so they're trying to encourage Cubic to do that, and anybody else to do that would want to get their implementation into a mainstream, widely deployed system.
Oh, very good for the suggestion. Thanks a lot for that. I actually, before, I don't know there is such organization who do this evaluation.
Internet Research Task Force, it's ICCRG, and I think I'm meeting with you tomorrow or something, and so I can give you the email addresses.
Okay, thank you very much. I will surely be happy to contact them and do the testing. Thanks a lot. So that is so we have that summary of TCP-Illinois, and now we complete the discussion on TCP-Illinois and go to the second half of the talk on the P2P streaming. We know that the video stream traffic has emerged, and it takes a lot of share of the internet bandwidth. And this is a figure from this report. It shows clearly that video has a large proportion of internet bandwidth, and the proportion is increasing sharply. And there are several delivery techniques for video traffic, including the traditional client-server single cast, for example, YouTube. The problem is that it is very expensive for the video content provider. And also IP multicast. That is very efficient, however, not generally available because the internet routers, most routers do not support this function. And also there is a proposal of overlay multicast or application layer multicast. Basically, if you think of two nodes, it's still a single cast, but in the overlay graph, the receivers can relay or forward to each other. So there is a tree structure on this overlay graph. And recently, there are a lot of P2P softwares which use P2P technique to deliver video. There are a lot of applications like PP Live, PP Stream, and they are currently for IPTV and video on demand. And later, there can be a lot of applications for multi-party video conferencing and online gaming. And for this IPTV and video on demand based applications, they have a lot of users. For example, PP Live, the data shows that in average, they have 20,000 users, and in peak time, they have more than 1 million users. This was the data from 2 years ago, and nowadays, the user number can only be much larger. For all these softwares, they provide low-resolution video delivery, and the streaming rate is typically in the 500 to 800 kilobps lane. And so we wish to improve their performance and get a high resolution video. And the natural question to ask is, how much room we have to improve from the current applications, and how do we do the improvement? So to answer these two questions, we need to get an idea of the streaming capacity of a P2P system. That is the maximum possible streaming rate that all users can receive. Now let's accurately define this problem. We think that is a fundamental problem for the streaming capacity in a P2P system. It is that given a P2P network with a set of sources, the set of receivers, and the connectivity between all these nodes, and given the source capacity, the peer capacity, what is the streaming capacity or the maximum streaming rate R that all receivers can receive? That is a streaming capacity problem, and it's equivalent to another problem. We call it minimum server bandwidth problem. For this problem, it is similar to before. Given a P2P network with a set of sources, set of links, set of users, and connectivity between the nodes, and given all the peers bandwidth and a streaming rate R to support, what is the minimum server bandwidth CS required to support that? These two are equivalent. Once we find the other, once we find one problem, we can solve the other very easily. And to start these two problems, we need to make a few key assumptions. Mainly, there are two such key assumptions. First, we assume that the bottleneck is only on the uplink users. The reason is because currently in the internet, the backbone is not congested, and congestion is typically in the access network. And for access network, typically it's asymmetrical, and the downlink bandwidth is much higher than uplink bandwidth. This assumption is made by almost all the researchers in this community. And also, we assume that we can ignore the peer churns in the time scale of streaming capacity. If there is peer churn, we assume it is in a slower time scale. And we can first start the streaming capacity for fixed set of users and include the peer churn later. So with these two assumptions, we can make some modeling of the P2P system. And we can build a multiple tree on top of an overlay graph model of P2P system. Basically, from this model, we can see that no matter this P2P system is tree-based or mesh-based, we can model them as multiple trees on top of an overlay graph. And with this model, to achieve the best throughput or the streaming capacity is equivalent to construct multiple trees that use as much peer bandwidth as possible.
When you say streaming, are you talking about more or less real-time content as opposed to like bulk file transfer?
Correct.
Correct.
And that's why you can ignore peer turns, because you're not going to have dropouts because it's live or something like that. Is that
correct? This is for live streaming. So now let's have a look to the background of the previous work. Previous work has done the streaming capacity study for small networks. For small networks, excuse me, there are two features for small networks. The first is that a small network can assume that the overlay graph is a full mesh graph. Any node can connect to any other node. And furthermore, small network, we can assume that we can build any kind of tree on top of the graph. There's no further tree construction constraint. Basically, it's that a node can have arbitrary number of children, and it can forward to all the other peers. So with these two assumptions, there are a lot of work on the small networks, including Jin's work and also Minghua Chen's work and all the others' work. And for all this work, they get a similar result. Basically, the result says that the streaming rate R has two bounds. One bound is the server bandwidth, because all the flows originally comes from server. So the streaming rate cannot achieve the server bandwidth. And the second bound is from the equality between total demand and total supply. The total demand is at least n times R, because there are n users, n receivers. And the total supply, at most, it is the bandwidth, the capacity of all the users. That is the server capacity plus all the peers' capacity. So from these two, so streaming rate has such two bounds. And the previous work shows that the minimum of these two bounds is actually a tight bound. And we can design multiple tree algorithms to achieve the minimum of these two. Basically, the idea of this multiple tree construction is to use up the bandwidth of all peers if this server bandwidth is not the bound here. So that is the previous work. However, for the previous work, all their tree construction, there is a property saying that for one node, if it is an internal node, it will upload to all the other nodes. So the number of children of any internal node is n minus 1. For example, here, we have one source and 3 users. We have several different trees, yellow tree, white tree, and red tree. And for any tree, one node is internal node and forward to all the others. It is okay if the number of users is small, but if the number of users is large, this is no longer feasible. We will see that later. That is the motivation for our work, to extend the study from small network to large network. For large network, there are two features. For example, if the network, the P2P uses a mesh-based algorithm, then the overlay graph is no longer full mesh. In this overlay graph, for example, for PP Live, there are more than 1 million users, but a node has only less than 100 neighbors. So you only have connectivity with your neighbors, and the neighbor number is very limited. So that is the first new feature for large networks. And also, the second feature is that if the P2P system uses a tree-based algorithm and constructs trees, the outgoing degree of any node in any tree cannot be too large. Here, outgoing degree is also called fan out. That is the number of children of a node in a tree. We claim that large fan out is not desirable. There are two reasons. First, large fan out means better resilience. If one node fails, it will influence all its direct children. So a large fan out means one single node failure will affect a lot of nodes. Second reason is that large fan out leads to a large playback delay. This playback delay is the time difference from a receiver playing a frame to the source playing a frame. This is at least the end-to-end delay from the source to the receiver. So we can show that if one node has a large fan out, then the forwarding at this node becomes the major or dominant force of the total end-to-end delay. For example, if there are m children for this node, then when it receives a small unit of data, it needs to duplicate it to m copies and then forward to its m children one by one. So for the worst children, this one-hop delay is m times b over c, where b is the size of the smallest unit. And the average delay is 1 plus m times b over 2c. So for some real data, typically the smallest unit cannot be smaller than 1,000 bytes. And a typical uplink bandwidth is 800 kbps. Suppose m is 10, then we can get that the worst per hop delay
is 100 milliseconds, and the average per hop delay is 55 milliseconds. These values are already very large, much larger or larger than typical propagation delays. So we know that a large fan-out is not desirable. And in a large networks, we should restrict the fan-out or the outgoing degree. For a mesh-based algorithm, we need restriction on graph. For a tree-based algorithm, we have restriction on tree degree. If the algorithm chooses a tree over mesh, combining mesh and tree, then we have both of these two features. Both the graph is non-full mesh and the tree is constrained. So we can see that a large network is characterized by these two features. And our contribution is the first work to study the streaming capacity on this large network with these two new features.
There's one other reason that large fan-out is undesirable besides the one that you mentioned, which is especially when you start to have high bandwidth and low packet sizes, which is that you start to become CPU bound. And around 1995, that was one of the constraints in the M-bone at the time, where the problem started to be that nodes that had a fan-out of greater than 10 started to have loss just because they were CPU bound in trying to, for very small packets, it's a large number of CPU cycles for the available bandwidth, meaning in order to consume the bandwidth, you'd go way past 100% CPU because all the replication was in software.
I see. Thanks for this new command.
That's usually not applicable in these cases because the ratio of CPU to available bandwidth
Upstream.
into which you can stuff the replicas is so extreme that it's incredibly unlikely that you're going to get near your CPU.
Yeah, if you have a relatively low uplink bandwidth, but if you have a relatively high uplink bandwidth and a relatively small packet size, it can be hit. But I agree that in general.
In practice for this, that doesn't necessarily apply.
And also, I mean, CPU is working in your favor.
Absolutely.
I mean, with this development, we still have the growth in terms of CPU power from core and stuff in.
Yeah.
So gradually, CPU bound is not an issue. Bandwidth bound is.
Okay, now let's continue. Let's see the challenge and our contribution in this research area. All the previous work, their trees has huge fan-out. So they are no longer feasible in the large networks. We need to design new trees for streaming capacity purpose. And for the general problem, on top of a general graph with tree constraint, even finding a feasible tree is NP hard. So this problem is NP hard. Why is NP hard? Let's consider a very simple example. Suppose the tree constraint is that you have only one child. Then this tree becomes a Hamiltonian parse. And in a general graph, construct a Hamiltonian parse or even determine whether there exists such a Hamiltonian parse. That is NP complete. So finding feasible trees is NP hard. And the streaming capacity problem is also NP hard. And also, the streaming properties in a streaming problem in a large network is a combinatorial network, combinatorial problem, and it has a lot of steps. First, on this graph, we have an exponential number of trees, and we need to enumerate all the feasible trees. And among all these feasible trees, we have to pick several best trees, and then do the rate allocation, split the streaming rate among these best trees. So there are a lot of steps, and each step it is very difficult to do. And also, for the most general problem, we can divide that into 16 classes in terms of session number, whether there's single session or multiple session, the graph feature, whether it's full mesh graph or non-full mesh, the tree feature, constrained tree or non-constrained tree, and whether there exists helpers. Helper is a node which would like to help to relay and forward, but does not demand the traffic. So for all these 16 possibilities and all these properties, all these challenges, we have made the following contributions. For one special case, which can model IPTV, which we can show that is polynomial time solvable, and we can get an exact solution for streaming capacity. And for the more general case, it is NP hard. However, we can find an iterative algorithm to get an approximation, to get an approximate solution for this problem. And in particular, if either the graph is not full mesh or the tree is unconstrained, we can get 1 minus epsilon approximation. If both graph is non-full mesh and tree is constrained, we can get a theta minus epsilon approximation, where theta is less than 1, and in a lot of cases, theta can be 1/4. Now let's start it from IPTV and then extend to more general case. For IPTV, there is only a single session, and if you choose a tree-based algorithm, and if every node is located in a single cell, then the graph is full mesh. And also, the source of the IPTV is typically a sit-in server. It's very powerful, so it can connect to anybody. It's not degree bounded, but all the other peers, they have degree bound. And we allow the degree bound to be node dependent. And for this IPTV case, we can show that there are some two new bounds. One bound still streaming capacity is smaller than the server bandwidth. And the other bound still comes from total equality between total demand and total supply. This is the total demand. This is the maximum total supply. Note that the change is that originally for each peer, it can upload at most CV. But now with this degree bound, the new maximum upload is the minimum of capacity and M times R. And we call this new maximum, we call it effective bandwidth. That is the new maximum upload a user can upload with this degree bound. And the minimum, for this maximum, for this streaming capacity problem, we see that the streaming rate R appears in both sides of this inequality. So that is very hard to solve. And we can start with the equivalent minimum server bandwidth problems. The bandwidth is lower bounded by streaming rate and lower bounded by total demand minus user supply. And for this problem, we see that all this R goes to the same side of the equality. And we can solve this problem first, and from this problem, get the original problem. And the two questions to ask are, first, are the new bounds still tight? We give a definite answer. Yes, they are still tight. And then, how do we show that it's tight? We need to design multiple trees to achieve this bound. And we have indeed designed multiple trees. We start from the simple case, M is 1, and then extend to M larger than 1, but everybody share a uniform M bound, and then extend to a non-uniform bound. So for all these tree constructions, the feature of these trees is that we try to use up the effective bandwidth of all peers if the server bandwidth does not bound the streaming capacity. So that is, there are a lot of details I don't have time to mention. So that is a high-level idea of IPTV case. So basically, for IPTV case, we can get an exact solution for streaming capacity. And for the practical impact, it has two folders. One, we can, with this streaming capacity, we can get a benchmark to compare all the existing algorithms, and we can know how much room we can improve from the existing applications. And furthermore, if the delivery, the IPTV is controlled by ISP, and ISP can use a set-top box to control the behavior of every user, then ISP can use our tree construction algorithm to provide a P2P and CDN combined solution for IPTV delivery. So that is for IPTV case. Now let's go to the more general case. You can have multiple session or single session. So we first start with a single session. For a single session, we formulate the problem to this primal problem. In this primal problem, we try to maximize streaming rate R, which is the summation of the tree rate for all trees. This tree, we consider all the feasible trees. If we don't select this tree, the rate allocation is just 0. And the constraint is capacity constraint. Here, Yt is the tree rate, and MVT, that is the fan out of node V in this tree T. So M times Y, that is the upload of a node in one tree. And the summation over all trees, that is the total upload for this node. The total upload is bounded by its capacity. So that is a primal algorithm. Maximize streaming capacity under the peer upload bound. And this primal algorithm is difficult to solve because it has exponential number of variables and it has linear number of constraints. This constraint number is linear. A typical idea is to convert the primal algorithm to dual problem. For this dual problem, we associate a price for each node, and then the variable becomes the price. So we have a linear number of variables. For this dual problem, we try to minimize the system cost, which is the summation among all nodes, the product of capacity and price. So this PV is a price. The constraint is that the tree price of all the trees is at least 1. Here, this is the tree price, and the tree price is the price of all the edges price, and it must be at least 1 for all the trees. So for this dual problem, we have a linear number of variants, and it's easier to solve, but still it's NP hard. And since it's NP hard, our aim is to find an approximation algorithm. This is an approximation algorithm. We use an iterative approach. We adapt the techniques from Giga and Kahneman in their traditional and classical work for multiple commutative flow problems. Our contribution is that for the first time, we show that the similar technique from the multiple commutative flow problem can be used to study the P2P streaming system. And the iterative algorithm is like this. Initially, all the nodes have a price being a very small number, delta. That's the same for everybody. And in each round, for given price, we try to find the smallest price tree. That is a tree with the smallest price. Intuitively, we try to put all the small price users to be the internal node, and make the large price users make these users to be the leaf node. So for this approximation algorithm, we have a child problem that is to find the smallest price tree. We can show that in some cases it's polynomial solvable, and in some cases it's NP hard. And after we find this tree, we will assign a maximum possible rate to this tree, and then adapt the tree price based on upload from V. This is the update rule. That is a new price equal to the old price times 1 plus epsilon times the upload proportion. Here, M times Y is the total upload, and C is the capacity. So My over C, that is a proportion of upload, that is a percentage of your upload. So basically, the more contribution you have make in the previous round, the faster your price will increase, and the more likely your node will be a leaf node in the later round, and the more likely you won't need to contribute in the later round. So with this adaptation, price adaptation, we can balance the load among all these peers. And all this iteration continues until at one point, all the trees have tree price larger than 1. When we stop at this point, we get a price vector which is feasible for the dual problem. And we hope that price vector we get is close to the optimal price. And furthermore, if the upload rate for a node V exceeds its capacity, we downscale that. Now let's show this algorithm with a simple example. Here, we have 1 source and 4 users. That is a graph for connectivity. That is very simple. And we assume epsilon is 0.1. That epsilon is in the adaptation, and use delta also to be 0.1. In the first step, we find the minimum price tree. Since all the nodes have the same price, any tree is OK, and we just pick a simple tree. For this tree, the maximum rate we can assign is 2. Then we assign 2 to this tree. And after we assign this rate, we update all the prices based on the law we have shown. And from here, the node 2 upload with largest proportion. So node 2's price increase the fastest. And 3 and 4, they are leaf node, so their price are not changed. And after we adapt that, in the second step, we still find the smallest price tree. Since node 2 has a higher price, and 3 and 4, they have low price. So that is a new tree with a smallest price. And we assign a maximum rate, which is 3 on this tree, and further update the prices. The update continues until finally all the trees, their tree price is larger than 1. Even for this simple graph, we have 11 such trees. The price vector must increase to a point that all these trees have a tree price larger than 1. And if that occurs, we stop the iteration. And once we stop the iteration, it is possible that the total uploads in all nodes or in some nodes exceed their bandwidths. If that is the case, we scale down. For example, in this figure, for this example, the capacity of all these nodes are 5, 4, 2, 6, and 3. And suppose total upload in these steps is these values, then we see that the maximum overshoot is 44/2 equals 22. Then we should downscale all the rates in all the steps by 22. After this downscale, the multiple tree we have arrived at is a feasible multiple tree, because with these multiple trees, all users, their total upload is smaller than their bandwidth. And after everything is done, after the algorithm, there are several questions we can ask. One, what is the total streaming rate we get from these steps? Two, how close is this total rate from the optimal rate? And also the time complexity, how much steps it takes to stop. These questions are answered in the optimality and time complexity analysis. For optimality side, we can show that if we can polynomial time solve the SPT's finding problem, which is a child problem in each round, then the mother problem is 1 minus epsilon approximatable. The total rate we get from the algorithm is at least 1 minus epsilon times the optimal rate. And if the child problem of finding smallest price tree is NP hard, and if we can find a polynomial time approximation with approximation factor theta is less than 1, then the total rate we can achieve is at least theta minus epsilon times the optimal rate. And the mother problem is theta minus epsilon approximatable. For this child problem, we have the following observations. If either the graph is full mesh or the tree has no constraint, then the child problem is polynomial, and the mother problem, we get 1 minus epsilon approximation. If on the other hand, in the most general case, graph is non-full mesh and the tree is constrained, then the child problem is also NP, and we can find an approximation. For most of the case, the approximation factor is 1/4. For the time complexity part, we can show that the iterative algorithm takes takes O n log n rounds, and it's polynomial. And finally, with these algorithms, the practical impacts are still two sides. First, it provides a benchmark to compare the existing algorithm, and also we introduce a price concept into this picture. So for mesh-based algorithms, when they do scheduling, they can based on price. That is too detailed. I will not talk about it this time. And this is a simulation validation. We have randomly chose a set of users and randomly pick their bandwidth based on the internet measurement. And this is for IPTV case. We can get the exact solution. This green curve is for exact solution, and this red curve is for approximate algorithms. It shows clearly they are very close to each other. And here is a summary. Before we do the summary, we have started the introduce a single session problem. For multiple session, we can still formulate the problem, and the formulation is a little bit different. It is basically a capacity region problem, and we can still use similar approach, convert the primal algorithm to dual problem, and use an iterative algorithm to find the approximate solution. And still, in each round, we need to find the smallest price tree. And the optimality result and time complexity result are similar to single sessions. And finally, we get such a unifying approach. Given a P2P capacity problem, we first see whether we have optimal solution. There are two possibilities. One is a small network. The previous work has solved that small network case. And for a large network case, and if it is IPTV case, then we can use algorithms to find an exact solution. If, on the other hand, it is a more general problem and it is NP hard, then we can use an approximate solution, change from primal to dual and use iterative algorithms. No matter it's single session or multiple session, for each round, we solve this SPT finding problem. And finally, we get the approximation, either 1 minus epsilon or theta minus epsilon. So that is a unifying approach to solve the streaming capacity problem. Any question until here?
So in this solution, do you still assume that each node has an upload bandwidth constraint?
Yes.
General. Does it hold for general graph topology? Or
yes, still hold. Still is that each node there is a bandwidth constraint, and the total rate among all the outgoing edges, the summation is smaller than its uplink capacity.
So if the topology constraint is not like that, it's more general than edge-based, does it still work?
No. So basically, this work is only on top of our overlay graph, and we don't consider the underlay physical links. That is the main assumption we make. The only bottleneck is on the access link and on the uplink case.
Is that because of the difficulty in finding the SPT under such model, or
It's not because of the SPT finding. It is because if we consider the underlay, then the bottleneck can occur in any place, and it's also there is a routing plays a role in this picture. There is a jointly problem. It's a joint optimization between routing and peer selection and rate allocation.
You have the current problem, like instead of saying that each node has an upload constraint, right? You have the age-based constraint, capacity constraints, and then you can do the dual. You end up having a similar smallest spanning tree problem, meaning cluster spanning tree problem, right?
Yes. Yeah, that's a good idea.
The SPT problem will change. So, for example, in this case, it will be min-cost spanning tree, and generally it will be a Steiner tree. So, the same framework should work.
Yeah, I guess I'm asking, are you exploiting something specific to the fact that you have upload in this constraint?
Yes, so only in the SPT problem, we use the fact, so because the uploads are on the nodes, the prices are on the nodes, not on the links.
Okay.
As you were saying, if the capacities are in the edges, then the prices will be on the edges and not on the nodes. It will be a spanning tree problem or a Steiner tree problem. But essentially, the same framework will work.
I would say that's a very important problem we yet to solve.
Yes, that can be our future work. Thanks a lot for raising this question. So, any other question until here? Okay, now let's summarize this talk. And in this talk, I have first introduced TCP-Illinois. It combines loss and delay as congestion signal, achieve a concave window curve. It satisfies all the requirements, the 4 requirements: efficiency, fairness, compatibility, and robustness, and it outperforms other algorithms. And in the second part, I introduced the problem of P2P streaming. Basically, we build a graph tree modeling of P2P system, and first start with the IPTV case, we get an exact solution, and then extend to more general case, we get an approximate solution. So that is the 2 works I have introduced. There are some other works I don't have time to talk about, which include 4CP, exponential red, stochastic matrix model, primal dual algorithms and their stability analysis, and also the modeling of delay and pitfalls of fluid models. So that is all my work. And for my ongoing and future work, it can be in several directions. For the TCP protocol design part, I plan to do a lot of internet real testbed testing for TCP-Illinois, and also I'm interested in the TCP variants, which can support real-time traffic and also support multicast. And furthermore, since I have developed a lot of TCP variants, I plan to make a unified structure to make it a multiple mode TCP stack. In this mode, there are a lot of modes. One, like if it is high-speed case, we use high-speed mode. If it is real-time traffic, we use real-time mode. If it is a low-priority traffic, we use a low-priority mode. And we also have a machine to automatically switch among this mode. So that is a bigger picture, which covers all my TCP-related work. And beside TCP, I'm also interested in UDP rate allocation and also the available bandwidth estimation. And so that is for protocol side. For the analytical model side, I have introduced the stochastic matrix model, but the existing work is only for single link. I plan to extend to multiple link. And for P2P streaming side, we have already analyzed the best performance in terms of throughput. The next step is the best performance in terms of queuing delay, in terms of playback delay. And also, we have ignored the pure churns in our system, in our analysis. We plan to include that later. And also, Yunan mentioned that we can extend our work to consider the physical link constraint. That can also be a future work. And finally, this work pretty theoretical, and I plan to design practical algorithms which can have good performance for IPTV and all for multi-party video conferencing.
So, and this is a publication list of my previous work, all the papers I'm first author. And this is reference list of all the reports or papers I mentioned in this talk. And thank you very much for attending this talk. And any question is welcome.
Right on time. I guess many of you will have opportunity to talk to Shao individually. Shao is a visiting researcher. If you would like to, if you're not on his interview list but would like to talk to him, please just drop me an email and I'll surely try to arrange such an opportunity. Okay. Well, thank you very much for your time.
Thank you for your time, and thanks for the good questions and comments.